Yeah, thank you very much for the kind introduction, Yassi. So hi everyone. Put the camera just if one day you see me and you want to say hi. It's a little weird because I didn't put the presentation in the correct screen, so I will look at the screen but not the camera. So I guess you have my best profile. So I will start being some general introduction to SYCL and maybe the more focusing on the difference between SYCL and CUDA and the familiarity between the two, so you can have a feeling. And then Abby will go more like automatic translation and cyclomatic and stuff like that. So I think I will do the handcraft approach and global overview, and Abby will go far more into details and stuff like that. So let's get started. Yeah, like I say, an overview of SYCL. So we'll give you the correct pictures and everything. I think it should take half an hour, 40 minutes, and Abby will take the rest. For the question, as I think Yassi says, whatever you feel more comfortable, I think yeah, putting your chat and stuff like that, more than happy to reply to your question. I think it's meant to be an interactive way if you have a lot of questions. So let's start. Let's diving into what is SYCL, an overview of SYCL. Maybe the first thing to ask, and maybe when I talk to SYCL, is like, is this thing really used? Is this thing a small thing on Aurora, nobody using? Why should I care? So Tim, in February of this year, put this nice graph, who is like we make a survey of the people using Aurora, and we ask them what programming models they use, and this is the answer. So you see 22 people are using OpenMP. Some people, I guess, are stuck in Fortran, they have no choice, or some people come really like Pragmas. I don't judge, everybody do whatever, but it's kind of weird, but whatever. And more seriously, 23 project or people say they like SYCL and they use directly SYCL. But I think where it starts being more interesting is, for example, we have 17 projects using cuCOS, but cuCOS as a backend use SYCL, right? So if you are using cuCOS, in fact, you are already using SYCL because SYCL is used as a backend for cuCOS. Same for some AI frameworks. So I'm not an expert into that. If I say some bad thing, please correct me. But I think PyTorch now is moving away from level 0 and integrating more into SYCL. So they climb up a little bit the layer of abstraction, and they go back to this thing. Oka, I know also is using SYCL as a backend. Same from Raja, and I think same for cuCOS kernel, who is using cuCOS, who is using SYCL. So you can read whatever you want in this graph. I think for me, the only key point is like SYCL is used. So SYCL is pretty robust, right? It's something really that a lot of people are using, a lot of people hence are debugging. For example, if cuCOS can use SYCL, you will have no problem using it in your project because cuCOS is kind of a super power user, right? They do like really a crazy C++ magic with template and stuff like that. So if cuCOS is compiling with a SYCL backend, at least you are sure that it will be good enough for your application. So this is maybe the first slide just to say, okay, it is used. We have user, and we have user now for the past, I don't know, 5 years. It is in production now, so more people are using it, but it is really something solid on it. Yeah, so before I would go some code example, I just show you, I did a quick Google of NV CUDA Hello World, and I think I put it here. Maybe I will put it bigger. So if you Google, yeah, I'm old school. No, I guess I should use a LLM, but yeah, habits are hard to change. So if you ask for Google to give you a hello world of CUDA, you have this kind of thing. So right, you have these functions that you need to decorate with global. Then you can use std printf. By some magic, it will be converted. Then you have this horrible Node C++ extension here with a triple chevron, right, to be able to launch your kernel. And then you synchronize over all the device, and then you return. So this thing is the kind of the hello world CUDA, so not even data transfer and everything, but just to look. I guess this is the first introduction to CUDA that we show to people. And for fun and profit, I ported to SYCL, and you see it's here. Let me put it big. And you see, it's. I think the first thing is like it's really similar. We'll go over more detail in the next few slides, but it is the same thing. So in CUDA, depending if you use CUDA driver or CUDA runtime, you have a notion of stream, who is maybe implicit. You have an implicit stream as we saw it previously. In SYCL, everything is really explicit. So you create a queue, an in-order queue and a stream are exactly the same concept. And then from your queue, you submit a kernel. So in CUDA, this is triple chevron with not C++. It is an extension, right? Just to lock you in their special thing here. You have a parallel for, so like a normal C function. And then here, like before, you have like, the number, the size of your kernel. You can define your iteration space. And here we do the same thing. So we put 1, 1, as in CUDA, 1, 1, 2 it was. And here we use a lambdas. It's maybe shocking for people who don't know new C++, but you get used to it. So it's just a lambda or just, function, anonymous function. So it's just a struct where you overload the parenthesis operator, and then you have a printf. And then in CUDA, in the example, you did something kind of ugly. You were just synchronizing over all the device, right? It's you assume you have a global state for all your device, and you were synchronizing in SYCL. It's a little more explicit, a little more how you can do it in the CUDA driver level. So you're synchronizing on the stream, on the queue. So q.wait, and a parallel for to replace the chevron. And that's it. So here you have you have the two code, and that's it. So this is how you port your code. You see, you have nothing to do. You remove your global. Oh, sorry. You remove your global. You put your kernel in the lambdas, and that's it. So, so I don't know why we got 2 hours. It was really trivial. Little joking, but yeah. So I think this is the key is to see that. So just to show you that it works, so let me show you to compile and to run. So resize. Let me put a little bigger here. So just to show you that they are not vaporware. Up. Sorry, here. Resize again. So for NVCC, you need to use NVCC, right? Because of course you cannot use Clang or stuff. I mean, this is not valid standard C++, so NVCC, and after, if I run hello world CUDA, it will print hello CUDA. For on Polaris, so right now I run on Polaris, so so SYCL is a portable, right? It runs in both CUDA and, for example, level 0, so in both machine, both architecture. So here what we use, the compile line, we'll use Clang. So Intel, Abby will discuss that more. So Intel have a fork of LLVM of Clang that you can use, and it is installed on Polaris. And so you just do Clang, and then you pass fSYCL, and then your target here, just to say this one can be omitted. But you say, okay, you want the NVPTX backend, and you rerun with the NVIDIA backend and CUDA. So it's if you are familiar with LLVM, it's a familiar triplet, as they call it, and then that's it. Then hello world and some include file for fun, because I have some dependency on the print. And then if I run hello world SYCL, impressively, it will print hello world CUDA, hello CUDA. So exactly the same. So this is why, yeah, so you see it's easy. So I see the question. So you just do module use of module files on Polaris, and after module load one API upstream. And this is how you do. And so the good thing is like, and maybe this is what I will suggest to people, it's far easier to port CUDA to SYCL on NVIDIA machine. So you can verify everything is working. You can even do it like kernel by kernel. You can mix and match CUDA and SYCL. So you can just port one kernel, one stuff, one malloc, and then you're good to go. And then you have a SYCL code, and you can move directly to Aurora without any doing anything. So yeah, for first example, you see it's not, it's really not impressive this way for the good thing. So now we'll go over a little more fancy example where we do allocation of memory, data transfer, and all of this kind of thing. So it's a little bit more challenging example, but you will see it's not that bad. So here, as I say, you create your queue, you create your stream. Here is just a slide to show you that you can have introspection, right? Of course. So a queue is running on a device. From this device, you can have some parameters. For example, you can have the device name. Something who is useful is, for example, to get a UUID. So you can verify if you are running correctly to the correct devices. And for example, if you do MPI plus X, MPI plus SYCL, you can verify that you have the correct binding of MPI rank to the correct devices and all of these kind of things. So this is always useful to have some properties. You can ask, because we are portable, you can ask some, does my device, what is the maximum memory of my device? Does my device support, for example, Atomic 64? It's not really useful in HPC because all the GPU we use that, but SYCL have also the spirit of being portable to the system or future systems, so you can have all this introspection. So first line, 6. So you see here, right, yeah, for the C++ people here, it is a template parameter here. So it will be nice when we get C++ 23, 27, that we'll be able to do for loop over type and everything. We could have nice introspection. It will make the code far easier. So because here, if you have multiple property, you cannot really create a for loop. Okay, I heard some people of you allocate memory. So you can do the same thing. You can just do, CUDA the alloc device or something like that. So here it's called malloc device. It's a template parameter. You pass how many global range, how many data you want, and then you want to allocate it on these particular devices. So you put a queue as a parameter just to say, okay, I want to allocate to the device associated to this queue. So here I show you malloc device. So malloc device is, of course, as the name implies, some memory were only accessible on the devices. You have malloc shared. I think in CUDA it's called managed memory, right? It's a memory we can move from the CPU and the GPU, who can accessible from the two. So whatever your preference, and it gives you a row pointer here that you can do whatever you want. So for example, here we'll use it in a kernel. So if you do q.parallel4, as I showed you before from the example, you can say, okay, this is my iteration pace. How many work item, how many iteration, how many thread in CUDA. Really despite this term thread, because thread is really an overloaded term. So in SYCL, like in OpenCL, we call it work item. And so we'll use, one work item is one unit of one lane of your SCM disk thread executing. And then, so your lambda will get an index, so no magic function to get some global function to get the index. So it's just you get the index from your lambda. It's a parameter of your lambdas, and then you can use it to index. So this is what you can do. So A, who is my pointer, and I index with the ID, and I put 1. So this guy is like a std iota. So I submit. All the submission are asynchronous, like in CUDA. So that means they are non-blocking, right? So you are free to do anything else on the CPU on the side. And so then you need to wait. Then you allocate host memory. Because I want to copy back the A device to the host. So I allocate my memory, and then I do a queue.copy. who is based on the yes CPU interface, the C++. So A host data, and global range. And then I rewrite, and then I free my memory with SYCL free. And so you see really nothing special. I see a question, two questions. So the compilation time and computing performance. So the compilation time, yes, is C++, so you pay a price at the compilation time is far more involved because a lot of template and everything. So we are working as a working group to try to reduce size. So as you see here, we have only one header file. So that means you include the old world. It's like if you have you know, like I think in C++, I think is one weird std header. If you take it, you have all the word, oh, you have everything, so it takes time. So we are working with the C++ committee, with the, sorry, the SYCL committee to try to split in multiple smaller header. So this is the first thing. For performance, computation performance, the at first order, you have no difference because at the end everybody is doing the same code, so everybody is calling a malloc device. It's a one-to-one translation to a SYCL, to a CUDA malloc device. At the end, everybody is using generating PTX, using LLVM and all of these kind of things. So you have absolutely no difference in performance. So this is the uh, first order explanation or first order justification of why you should not have any performance difference. At least semantically, you can express exactly the same thing in SYCL that you can do in CUDA. Of course, bugs exist. So if you have a bug, it's a bug, right? So you should just report it and everything. But I think Abby will show a lot of examples that you have one-to-one exactly the same performance. Of course, you can have like subtle difference or stuff like that. But at least in the semantic point of view, we are not aware of anything that you can express in CUDA that you cannot express in SYCL. So this is, yeah, code example. So in a nutshell, we have more example if we want later, or if you have another question. Oh, sorry, what is a global range? Yeah, it's a good question. Global range is the technical term, I mean the standard term that we use in OpenCL or in SYCL. It comes from OpenCL. It is really the number of thread, right? It is the size of your iteration space. If you come from MPI, I think MPI is a more easy mapping is the, for example, the size of your COM world, right? It is a number of process is your MPI COM world, so it's exercise. It is your iteration space. So for example, here, if I global range is 20, I will have the size of my array will be 20. So you're right, I should have defined it. I copy paste too fast. Uh, so yeah, this guy, you can just imagine the size. What is the meaning if equal size? Oh yeah, so this one is just a C++ allocation, right? It's just to say ID equal, so it's just a memory allocation. So you just put the value of this ID. So this one, it's a SYCL index, but we'll show later it can decay to a valid int. So this one it's a little more complex, but whatever. It decay to a int, and then so you can use it as an index. So it's really like a memory assignment. So in a nutshell, at least you can see it like this way. I think it's a nice mental model. At the first approximation, I think it's a nice mental model. Yeah. Uh, you can just see SYCL as a nice C++ wrapper around CUDA API. Oh yeah, sorry, this guy. Yeah, so sorry. So this thing is a lambdas. So if you are not familiar with lambdas, as I say, it's a function will capture everything. So it's an anonymous function and you can access the outside scope. So for example, here I can access ID and I can access A and A have been defined outside of the lambdas. So this little thing means I want to capture everything from the outside by value. So I copy the value of A directly in my lambdas. You can capture also by reference, but it will not work by reference. because you cannot, this pointer is only valid on the device and you need to copy the real pointer. You don't want to do any translation and stuff, so you need to compile by values. Yeah, so good question about the CUDA is more than the API. Yes, I will discuss later. So we start with the API and it's correct, and then we'll go later on the thing. So yeah, so a nice C++ for the API. For the kernel code, somebody have a question and it is exactly the same thing. It's really, really similar. Abby, and I don't know if Steve is here, but Abby have far more experience. And yes, so you have like shuffle, sync thread, shuffle down, shuffle. We have even subwarp, so we call it subgroup. So you have exactly the same thing, and the mapping are just one-to-one. So if you look at the assembly, if you have a group, Abby will show that too. So you can have a subgroup, and you do subgroup.sync. And if you look like at the PTX, you will have the sync thread intrinsic. So it's really a nice C++ wrapper over PTX. And also you can have like inline PTX and all of this kind of thing if you really, really want to get deep. But I think right now we never see any intrinsic. The good thing is because GPU are kind of stupid, right? This is maybe what saves us. It's like GPU cannot do that much stuff, right? You are kind of restricted on what you can do on a GPU. So it's pretty easy to be portable across GPUs because everybody has this kind of barrier, shuffle down, shuffle up, all these kind of things. So this is what you use and this is what you have to. And yeah, as I say, one of the big advantage, it's an Intel, NVIDIA, and AMD, so it's portable uh, everywhere, at least by the amount of love. So of course at Argonne we are far more focused on Intel, so we debug, me and Abby work a lot on the Intel backend, the level 0 backend. But Intel, with their partnership with Codeplay, invested pretty much a lot on NVIDIA. So this is why my example was on Polaris. Abby have a lot of example on Polaris and a lot of experience. So it worked. And on AMD, the support, I think we need you guys to ask if you are running on other machines that you want it, and it will be nice. So it's working, but I think you may have more, as we discussed before, like bug, performance issue. So a quick question. They say MPI plus CUDA, synchronize multi-GPUs. Yeah, so we can discuss that. I will replay by stuff, lever or if so say. So the question is how you handle multiple GPUs if you do in SYCL, and the question is it more or less have nothing to do with SYCL. So, for example, you have two choice. One is you can set, for example, from the outside CUDA visible devices, for example, on Polaris. So that means each rank will see only one GPUs, and then you will use MPI to be able to share transfer between GPUs or stuff like that. So this one is maybe the most standard way, is you bind each MPI rank to only one GPUs and you play with the visibility from the outside. So each SYCL process see only one device. But you can do far more complex stuff in SYCL because you can have multiple queue targeting multiple devices and then you can synchronize. And you can also it's possible to have queue who target also the CPUs if you want to be extra fancy. So now you can have multiple queues, a queue for the CPU, a queue on the GPU, and you can mix and match. So you can share the same kernel between the CPU and the GPUs and executing both at the same time. And you can use event to create a DAG and all of these kind of things. I can share some more code later if people are interested. So of course you have some difference and some similitude. I want to don't say it is a one-to-one mapping. You need to do some work. So for example, here I show a queue. A queue, uh, we come from OpenCL, and for other reason, the fact that I think it makes more sense to be by default output order. But so a queue in SYCL by default is out of order. So that means if you submit, if we take this code here, and if I remove the weight here, I just submit those two, you don't know in which order they will execute. By default, queue in SYCL are out of order. The reason for that is performance. That means, for example, if I do a parallel for and a copy, both will execute at the same time because, of course, I can do a PCIe data transfer at the same time I execute a kernel. So by default, we are out of order. If you come from CUDA, in CUDA you don't do this way. In CUDA, the streams are in order, and if you want to have concurrency, you need to be uh, your work scheduler, you need to be your scheduling algorithm. So you need to yourself say, okay, this queue is for the data transfer, this queue is for the thing. And I found it, I mean, scheduling algorithm, right? It's 40 years of research. It is a lot of things. You need a PhD. So, but in CUDA, you need to do it yourself. You need to create multiple queue, multiple stream, and after submit. And of course, we are not ready. We give you the possibility of doing that too, so you can create in-order queue. So you can pass a property when you create the queue, your constructor. So your queue will behave exactly like a stream. They will be in order. So this is what I think Abby will discuss that later. It's like stream are in order queue, but by default we are out of order for preferences. So this is maybe the one of the big difference when you come from CUDA is this in order, out of order queue. But it's easy to change. It's when you create the queue, you just pass a property and you're good to go. One another differences is you need to pass the ID to the kernel. When you have, as I see in your Lambda, you pass the ID, where in CUDA, like in MPI, you have like a magic function, a free function as we call it, with get thread ID or something like that, I think it's called, where it just gives you magically from, and so it's not the default on Intel, on SYCL, sorry. I say work item. A work item is a thread, so a different nomenclature. So we use OpenCL way. So a thread, a CUDA thread, it's a work item. A CUDA warp is a work group. And we have the same kind of, you can only synchronize in thread inside the same warp. So you can only synchronize work item inside the same work group. You cannot synchronize two work group together. So you cannot synchronize two warp together. As we say before, and it was a good question, for the not the CUDA API, but the CUDA C or CUDA C++ or whatever they call it, we have exactly the same capabilities, group barrier, shuffle, and everything. So it's just a different namespace. That's it. It's just SYCL item.barrier and not whatever thing thread. One thing who may beat you also is like if you do more than 1D, for example, 3D, like you can do in CUDA and in SYCL, the order of the fastest index is different. We follow, for better or worse, C++. SYCL tried really to be close to C++. So this is why we choose to follow the indexing of C++. And for reasons I don't know, it is a reverse than in CUDA. So please, for this one, don't blame us. Blame C++. I don't know if Nevin is our representative to the C++ committee. So blame him. It's not our fault. We can discuss later if people are interested, but you have a nice dependency chain with events, so you can just, each kernel give you an event, each parallel for each command give you an event, and you create a nice DAG, a direct acyclic graph, to be able to express really complex dependencies, either between in-order queue or inside an out-of-order queue if you want to have like, if you don't want to do dot weight each time, because dot weight has a pretty big overhead, and you really want to minimize the number of sync points you are doing, event and dependency are a pretty clean way of doing it. It's like, for example, in OpenMP, you have, this OpenMP how it's called, depend in, depend out. So an event allow you to do this kind of nice thing. And last but not least, you have a nice interop with a native backend. So in our case with CUDA, so it's pretty easy to get a native object. So from the queue, you say, okay, give me the stream. Or you can use like CUDA malloc pointer inside your kernel and it will work. All of these kind of things. So it's pretty easy to mix and match. So you can really port your code, your CUDA code to the SYCL code running on an NVIDIA machine really step by step. So it's pretty easy. I like it. As I said, we have some difference and we listened because some people were already, it was not really enjoyable. For example, passing the ID everywhere was painful. You design all your code to be able to get this ID, and the refactoring can be a little painful to do that. So we are working part of the official SYCL working group with part of Chronos, so we develop a new set of extensions that we put on the spec for you to use and for you to give us feedback before we merge it into the spec. One is this free function query, so it allow you to just do get item or get work item or stuff like that. So you have it, you don't need to pass the ID, and this is what Cyclomatic is using. So you can, it really is the porting from CUDA. Personally, I'm not a big fan of this free function query. I find it not pleasing intellectually, but we understand totally that it makes sense when you port your code and it's far more convenient. So we put it in the spec. Same, we were missing in CUDA, you can do, you can verify if the stream is empty or not. We were not having, we didn't have these capabilities in SYCL, so we add it as a KHR. Same also, I told you, you can have a DAG, you can create a graph, but you can do that in CUDA too, and in CUDA the goal is really to lower the latencies. In SYCL it was not really the case, the latency was still high, so we develop extension to lower the latencies of submission, and one of them is this graph extension. And printf also, I show you an extension that I developed, and the official way, I mean printf is pretty complicated. You need to allocate memory and all of this kind of things. So we have an official way using like stream and stuff like that, but it's really convenient for this. It's not convenient for the same function of free query. So we want to have a free function printf or format or whatever is new in C++23. So we are working on that. And if people are interested, please let me know. We can work on that. And I think that's it. That's it. Abby told me 40 minutes. I did first 55, so perfect. And yeah, just so let's finish with this one. So it's really the big difference is this queue. I should have put the slide. I can show you maybe quickly with in order queue. If I lose my node, but I think it's okay. And I have in order. So here 6 in order. And we'll finish on that. So ready to show you how to create a stream. I will show you two code. So you see here, when you create the queue, you just say it is an in order queue. So that means now everything, it really be like a CUDA stream. So I can do my parallel for, and I can do my copy. And I know my parallel for will execute before my copy. My copy will not start after the parallel for. So it is this kind of nice, from CUDA point of view, really similar. And for the question about more like C side, I mean language side, I have where it is this thing, the share local memory and stuff like that. So I want you to show you that. So for example, here, we can get the global ID, local ID. You can use, for example, clamp and all of this kind of crazy thing. And then, for example, here, what I do is I use some share local memory to be able, here I want to swap some values and to avoid race conditions. And I need to synchronize between all the work item of my work group, between all the thread of my warp. So I have this barrier. And you see here it's really similar to Sync thread. It looks like just far more C++y, for better or worse. I think it's a judgment call of what you prefer, but you see here, and you have a way of allocating share local memory. You can do like, because it's C++, you can do this crazy, you create an allocator, you pass it to your vector, and now you have a vector that you can use on the CPU and on the GPU, so you don't need to deal with data transfer. So you see here, I have a vector, I use it on the CPU, and then I use it on the GPU, and I don't need to do any kind of data transfer copy and everything. So you should or should not do it, I will I will not tell you, but I think it is a possibility. The fact that it is C++ allow you to do a lot of things. For example, we have also an example with mdspan if you want to use. So this one, if you want to do sdspam to you don't like row pointer because we don't live in the 70s anymore, and you prefer to use mdspam from C++73, you can just use mdspam inside your parallel 4. You have no problem, everything work, and you can just do mdspam stuff inside your parallel 4. So of course in tutorial we need to show you only the basic one, but C++ allow you to do stuff like that. And that's it. I don't know, Abby, do you want to take, or do you want me to answer some question? What do you want to do? How long do you want to have?
Go ahead and quickly answer the last two questions, and I can share my screen in the meantime.
Okay. So Tim, variadic function to SYCL? No, I think we'll never do variadic function. I think what we'll do is template it, maybe. But I think C variadic are a nightmare. I don't think we want to support. So I think no, but variadic template, yeah, should be possible, but not variadic C. SYCL use lazy DAG. Wouldn't that reduce the latency of kernel launching? Yeah, so it's a good question about the latencies of submission and the greediness. I think it's a complicated question, but in fact, no. So the specification doesn't say anything if we are lazy or greedy for the latency submission. I even have an example here. So we don't say anything on the spec. So some implementation are lazy, some implementation are greedy. So the big question is like, when you do your parallel 4, does it execute right now, or do it need to wait that you call dot wait? And the fact it is not the case, so it depends. So right now we don't have, you are really just at the mercy of the implementer. So if we want to give you a systematic way of gaining back the latencies, we need to find something, and it is in the graph. But we can discuss more. I'm really interested in this question, and we need more than 30 seconds to reply. But yeah, it's a good question, and sadly, right now, it's not the case. What part of STL is available on the device in SYCL? It's a good question also. Mostly everything with not allocating memory. And sadly, we don't have a list anywhere. So I think most math in COS and everything Intel provided. The spec answer is none. In theory, everything you should use, it is in the SYCL namespace, because SYCL should be able to be implementable as a library, at the library only. Some people did that. And in this case, you have no control over libc++. So that means you cannot know if it is possible to use libc++, right? Because, for example, I don't know, maybe syncos will throw an exception and stuff like that, or allocate memory for a weird reason. So as a library, you have no control. So for portability, everything is in the SYCL namespace. But Intel is not a library on the implementation. Intel, in this case, is also developing and shipping the libstdc++. So Intel, like NVIDIA, can do horrible trick like this, because they are both the compiler and the library, and they can interpret printf, and they can replace the libc++ printf with the CUDA printf and stuff like that. And so for Intel, a lot of things. For example, as I show you, you can have used syn, cos, clamp. So everything, in theory, everything who doesn't throw and doesn't allocate memory should be able to use on the device code. Great to see performed about customizing a curve for shared memory. Yeah, so this one now, in theory, no. Oh yeah, it's still complicated. It's because you have no control on when the memory will happen. You can prefetch and you can do all of this kind of thing for the shared memory. So this is why this one is more a personal concern. For me, shared memory and managed memory, it is the porting. So you save porting and you waste hours and days and months for performance tuning because now you don't know where the data transfer happens, so you can profile and everything. So I think it's a trade-off. 1 DPL for an area. Yeah, and then a shared allocator for an area. Yeah, so now you need to have fun. You have a lot of research if you want to have a spatial allocator, an area allocator, a thread-aware allocator, all of this kind of thing. Now you go back to a typical allocator. So this is why I try to to stay far away from that because it look good in one slide. Using it production is a lot of work. So I think it can be a nice research project to develop an area locator if you want to handle that yourself to avoid the fragmentation of memory and all of this kind of thing. I think it's a good. For the example, it doesn't work is because you are on the logging node, and on the logging node you have no GPU, so it cannot run. You need to be on the node. And yeah, so Abby, I'll let you continue, and I will be there to continue replying on chat. Thank you very much for a lot of interesting questions. Sorry to to not be able to go on more details. We are a little time constrained, but I will more than happy to continue talking to you on Slack or stuff like that. I like this kind of thing, so you will never bother me. I'll let you continue then, Abby.
All right, thanks, Thomas. Can you hear me?
Yep.
Yeah.
Okay, great. So in this section, I'll talk about some examples and what is the motivation behind using SYCL. Of course, the first motivation as we have is ALCF Aurora, which is an Intel GPU-based machine. So most of the programming models like OpenMP work, but SYCL is its primary programming model. So this is just a space of DOE machines, which and with its programming models. First, I would talk about the native programming models per se, and the nature of GPUs it has, and the counts. So as you can see, there are like a bunch of machines with the different vendors, and each comes with its own programming model, CUDA HIP. So and the SYCL comes here in the place of portability. So and of course the question is productivity and performance.
Sorry, Abby, are you sharing something? I am the only one to not see stuff.
No, I see them.
Oh, okay, so my bad. Sorry to interrupt you. Then I will try
No,
to.
it's
that's
okay.
okay.
You have to be on the Abhishek screen. So
Oh, I see.
You have to stop
Okay,
screen sharing.
yeah, thank you.
So SYCL is like a portable programming model, so you could run on all three vendor GPUs, and of course CPUs as well. So this just shows how widely SYCL can be deployed. This is a quick sneak peek of Aurora architecture. So you could see how many nodes. It's over 10K nodes with the count of GPUs and CPUs. It's over 2 exaflop performance. I wouldn't say FP64, but it's over 6 exaflops. There will be an interesting talk tomorrow about how to optimize for Aurora and how to efficiently run on Aurora. And this will be done by Vitaly. He's the performance wizard. These are few notable or a handful of applications that uses SYCL at the moment. These are mostly developed from the Exascale computing project stage. So these are some of the applications from HPC space and as well as AI. So as Thomas was mentioning, why use SYCL? And so one should mention here that SYCL is not a programming model, it's a language specification. So there are multiple vendors like Intel, CodePlay. They take this Intel SYCL specification and they come up with their own implementations. So one such implementation that we're talking about today here is one API, DPC++. This is an implementation of SYCL from Intel. There are other implementations as well, which I'll show in the next few slides. And of course, SYCL is a C++ single source programming model. So you could use the same source code for both host CPUs and the device GPUs. I'm here referring to the CPUs and GPUs, but there are examples where folks have used SYCL on FPGAs as well. So it's just not limited to a few vendors or few hardware. So there are two distinct memory models, and USM and buffers. We would not talk about buffer objects. This is a way to manage memory. USM, and on the other hand, these are simple way because of their nature. They look like a raw pointer. So USM is nothing but unified shared memory. So I would refer folks to look at the SYCL specification document. So all the slides and the examples that are ported from CUDA to SYCL, they would be naturally converted with USM interface, which employs pointers. And of course, it's an asynchronous programming model, so one can overlap device compute, copies, and host operations, because this is a part of using SYCL, and the DAGs play a great role in that. Of course, we cannot ignore the portability benefits. And since we're talking about portability, it's just not about functional portability. One needs to consider about performance because of it's deployed on several hardware architectures. And when you're talking about portability, you cannot miss productivity. So you don't want to write a lot of code, which diminishes productivity. So this is where 3Ps comes in. For SYCL, it's portability, performance, and productivity. This is a quick snapshot of what are the compiler implementers look like. Again, this is an outdated graph, outdated figure, I would say. So for the scope of this talk today, I'll be mostly concerned about DPC++, which is based on Intel LLVM fork of Clang, and configured as one API, or marketed as one API. So this could run on any CPU and currently on Intel GPUs via level 0. So level 0 is the driver that we use to target Intel GPUs. It can run on NVIDIA and AMD GPUs as well with CodePlay plugins. So Polaris has its own module where it could target to NVIDIA GPUs, and I believe ALCF Frontier has a SYCL compiler DPC++ module, which can target AMD GPUs as well. So there used to be a compute CPP implementation. So CodePlay has its own implementation, but that's now been absorbed into DPC++. So both are not distinct. HipSYCL is one such effort from the University of Heidelberg. So this is an academic effort. So HipSYCL is now renamed to Adaptive CPP, if you hear that. So you will find all the both these two implementations on Polaris, DPC++, one API module, and as well as HipSYCL as Adaptive CPP, if you want to check it out. So talking about some basic fundamental paradigms in C++, we need queues and contexts. So these are the fundamental objects where how you submit the job or a task to a device. When I say device, I'm not really specifically talking about GPUs. It could be a CPU or a GPU. So these are SYCL queues, which actually provide the mechanism to submit work. So the work can be a copy operation or a kernel launch. Again, I'm talking about here about a device or a sub-device. So when I say sub-device, you can partition a given device, if it allows, into sub-devices. Folks who are familiar with the like NVIDIA's mid-mode, where you can partition a given GPU into several components. So similarly, you can partition a device into sub-devices. This is via programmatically in SYCL. SYCL contexts are not so well known. it's not so visible. Similarly, like CUDA context, if you have heard about it, there exists CUDA context or cuContext in the driver APIs, but it's not much used in the runtime API. So SYCL contexts are similarly overlooked, like CUDA space. These are the contexts that tie to a queue. So what is the difference between a SYCL queue and a context? So talking about context first, because these are much higher level abstractions. SYCL contexts are used for mostly resource isolation or sharing. Let's say you have a node with 8 GPUs or 4 GPU. You can create a context for each of the GPUs such that each of the GPU has its own space and these are isolated. On the other hand, you could create all the GPUs, all the 8 or 4 GPUs on the same context. This will allow resource sharing. So it's about like whether you want resource allocation or sharing. So when you do an isolation, it'll be very hard to do a peer-to-peer copy. If you do a sharing, you can have a peer-to-peer. This is just an example of what the resource isolation or sharing means. I mean, not literally in the meaning of peer-to-peer copy, which has a different meaning. So SYCL context it consists of one or multiple devices. As I was saying, if you have one device, it's just isolated to that device. If you have a SYCL context for all the devices share the same SYCL context. So on the other hand, you have a queue. So someone asked a question about like, what does CUDA stream look like? So if folks know, CUDA stream is an FIFO interface, first in, first out. This acts like an in order operation. So it's like a pipeline with a FIFO in nature. SYCL queue is similar to that if you make it that way. So as Thomas was mentioning earlier, SYCL queue by default is out of order. So if you submit some work to a SYCL queue, it can just launch in any order of its own. It's dependent upon the hardware scheduling. So this can lead to a potential error when you in the earlier days of Aurora and the SYCL development. The tools that ported from CUDA to SYCL context did not take in order or out of order property into an account. So most folks used to get a wrong answer, and that could be fixed with in order because CUDA stream is in order by nature. It's a special property that you have to assign it to a queue while creating that queue. So this is a snapshot of a queue and out of order, and how does it behave in an in order. So it all depends upon how you submit the tasks. So let's say a kernel A, a kernel D depends upon B and C, and B and C individually depend upon A. So you need to have some sort of a dependency. If your kernel is not launched in order fashion, so any of these 4 kernels can submit and can be launched, and this can potentially lead to an error. But on the other hand, you start with kernel A. Now you have an option to run kernel B or C. It doesn't matter because of its isolated dependency. So B or C does not matter. You have to have an explicit dependency established if you are using out of order. And kernel D should come last, only after B and C finish its computations. So that's how out of order in order queues loosely work. I haven't gone into much detail, but I'll talk about like how do you create an out of order queue. So if you don't mention anything, if you don't specify any property, that's an out of order queue. If you specify a property and in order explicitly, that will be an in order queue. So as you see here, I'm explicitly mentioning GPU selector, which means target the GPU devices on the platform, on the node. So you can have it as like a CPU selector that would target CPUs. So that way you can create queues targeting each device. And someone asked the question, how can I use SYCL for multiple GPUs? So if you have a queue for each device, it could be a CPU or a GPU, it could be in order or out of order fashion. That way you can target kernels launching on multiple devices concurrently at the same time, taking advantage of the hardware resources. So what is a device? It is similarly like a CUDA device. You set the device, you get the device in CUDA. You don't exactly have the same semantics in SYCL, but SYCL do provide devices as well. So SYCL subdevice, as I'm saying, is like a CUDA MIG mode. or in OpenCL, if you're from OpenCL land, it's from OpenCL subdevices. We have coined two terms, Intel coined two terms called explicit scaling and implicit scaling for Aurora. On Aurora, you have PVC GPUs, 6 of them, but each one of them can be split into 2 subdevices. And that's what explicit scaling means. And this is what happens on ALCF Frontier as well. Physically, there are 4 MI250X GPUs, but they are now they are split into 8 individual devices. So explicit scaling is nothing but partitioning a device into its subdevices. The reason could be anything. Most of the primary reasons are like the NUMA boundary and the performance latency that one could avoid when you cross the NUMA boundaries on the actual chip. Implicit scaling is nothing but you just use the physical device as it is. Instead of partitioning, you just use the device as it is without any partition. So this is a quick snippet on how you can partition a device, and explicit scaling is known to have better performance just because you don't cross the NUMA boundaries. Implicit scaling is the traditional old way, and this is the way how you can query all the GPUs and loop over each GPU and create its own queue. You have SYCL events. These are similar like a CUDA event. Events are usually used for tracking the work that you submit to a GPU or a CPU. So these events are like bookkeeping, and they work similarly. I mean, events are and for timings as well. So these are very similar to CUDA or HIP timings, if you're very familiar with that. So SYCL runtime inherently creates a DAG. So we don't really see the DAG, but there are ways to actually visualize the DAG, obtain the DAG, and visualize the DAG. So SYCL mostly works with the dependency infrastructure and uses SYCL events to create the DAGs. And these events provide a way whether my particular task is complete or not. So there are several. So when I say task, there are predominantly 2 tasks. One is kernel submission, one is data operations. So each and every data operation, like moving data between CPU and GPU, gives you an event as a return when you submit a mem copy. This event return can be used to check if your particular task is complete or not. Similarly, for a parallel for this is a kernel launch, like a triple chevron in CUDA. The event return can be used to track the completion of this event. As you can see, there are like an event dependency events. So these are nothing but events that are acting as a dependencies. So in order to copy this start this copy operation, this dependency event first needs to complete. So you can create a chain of dependencies by passing an explicit event as well. And similarly for a kernel launch. So talking about porting from CUDA to SYCL, these are just terminologies. So you have thread, block grid on the CUDA side, which boils down to work item, which is the smallest part of the programming model. Work item is nothing but a thread. Work group is a collection of work items. So you can think of it as a collection of threads. ND range is just a global iteration domain. So you have grid with 3 directions. You have an ND range with 3 directions. So similarly, like in CUDA, you have 3 different directions, 0, 1, 2. In SYCL, you have X, Y, Z. So a grid is like an array of thread blocks from a CUDA perspective, which gets launched onto the kernel. And CUDA warps. So these are the very advanced intrinsics that one could use. Warps fall in between a block, a block and a thread. Warps are nothing but a collection of threads, but not a huge collection. So warps is like a SIMD lane or a SIMT lane. So a collection of 32 threads on the NVIDIA side is called a warp. So when you launch a kernel, mostly it will be launched in terms of a warp. Similarly, on the SYCL side, you have a subgroup. So it's not a full work group, it's a subgroup. Subgroup again is a collection of work items. On the NVIDIA side, 32 is defined as a number, so it's predefined. On the SYCL side, it is not predefined. So such an assumption could be very costly. So if you run on NVIDIA GPUs, yes, no doubt it is 32. But on Intel, it is not necessarily to be 32. It can be 16 as well. Similarly, on the AMD hardware, it is 64. So you cannot make an assumption for what is the size of a warp in SYCL or a size of a subgroup in SYCL. This is the convenience with SYCL, where it gives you flexibility to query the warp and actually write the intrinsic space off of that. And you don't make any assumptions on what the size of the warp is, where you make such an assumption while writing some of the warp-based intrinsics in CUDA side. So most probably, people who are familiar with CUDA write one such function called block reduce, where you loop over 32 threads and do a reduction. You don't do such a thing in SYCL because there is an API for that, which you can directly use with the subgroup. So it's called subgroup reduce. It does not query, it does not assume the size as 32. It just queries the hardware, underlying hardware, and then applies the same operation. Why use a subgroup? So subgroup, as I was saying earlier, it's like a subset of work items. So blue is like a work item, a collection of these threads are a small collection of these work items are called subgroups. Bunch of subgroups can be called as a work group. A bunch of work groups can be combined as an ND range. This is the global iteration space. As you can see, most of them are in 3 dimensions. Subgroup is not. Coming to the memory model, we were just talking about like the execution model. So how to launch the kernels, what would it involve while launching the kernels, and how would it map onto the hardware? Now we would talk about the memory aspects of it. So this is so there are similar one-to-one mappings between CUDA and SYCL, loosely speaking. So there is register memory, which is very local to the thread. So similarly, you have a private memory, shared memory, which one uses heavily in CUDA side for better performance. You have similarly for in SYCL, which is called local memory, shared local memory, and you have a traditional global memory as well. This chart from the SYCL specification provides you 3 different allocation types. So you could do a malloc on device, host, and shared. The first one, device, is nothing but like a CUDA malloc. You just allocate it on the device. Host is like a pinned memory allocation. So on the CUDA side, you pin the memory for faster transfers between CUDA and device, or a page locked memory. Similarly, on the SYCL side, you have a host memory, which can be accessed by both host and device, but not migratable to device. Shared is nothing but like all the host and devices has visibility of it, and it could be migrated between host and device. Shared is a convenience. It's like a managed memory on the CUDA side. The runtime would move the data for you. So you don't know where the memory is first allocated, but when you access it, the runtime behind the scenes will move the data for you. Similarly, like what CUDA does. So this is how an API looks like for the CUDA malloc, part of a global memory. If you do an allocation, again, we're all playing with pointers here. I should mention here that any SYCL API that you use, it could be memory allocations, deallocations, data transfers, or kernel launches. Each one of them would employ a Q as an argument. This is the reason, because Q is tied to a particular hardware. Forgive my mistake. So Q is the object that you can connect it to a particular hardware. So you need to explicitly pass a Q for all the different tasks that you do. As I was saying, you can index CUDA in XYZ dimensions, but on SYCL side, you index with 210. So this is the most common pitfall or the mistake that we initially did. And of course, the porting tools adapted it later. CUDA is based on C, but SYCL is based upon C++. So there is a difference between column major versus row major. So what is the fastest indexing dimension? And those are the fundamental differences from the language perspective that brings these inversions. So you have XYZ on the SYCL side, you have 210 on the SYCL, sorry, on the SYCL side. So I'll talk about the math libraries because we just don't want to talk about the language. We want to talk about the libraries as well because that's how most of the projects are written or are supported with. So there is something called as one MKL project based upon the DPC++ implementation from Intel. It's an open source implementation and also has a product implementation, which is a closed source. So one MKL can run on all three hardware, NVIDIA, AMD, and Intel GPUs. The open source implementation is open for NVIDIA and AMD, but not for Intel. So when you install something from an Intel One API based kit, you will get an Intel product One MKL implementation. This is closed source, runs on Intel GPUs or hardware. You can clone this open source One MKL project. So this is called a One MKL interfaces project. So just to differentiate between One MKL and One MKL interfaces. One MKL interfaces is a project that targets NVIDIA and AMD GPUs. But again, irrespective of what project you use, the same SYCL One MKL APIs works on all three hardware. And of course, you can also target a host CPU interface, which piggybacks on Intel MKL if it is installed on your system or just netlib underneath the scenes. So if you use SYCL One MKL project and run on NVIDIA GPUs, it would just piggyback on cuBLAS, cuSolver, cuRAND, or whatever the domain of math library that you choose. Similarly with AMD, this is the current state of One MKL interface project. There are some issues with the rock solver. It's still being developed or bugs being resolved. So it's not so stable as one would expect. But the rest of the domains in the linear algebra space are all covered. So how do you port an existing CUDA project to SYCL? So there is something called as DPC++ compatibility tool from Intel. This is the tool that you would use to port a CUDA application to SYCL. It does a pretty good job at porting 90 to 95% of the code automatically and puts a bunch of inline comments to help developer later to see what has not been ported, and if it has been ported, are there any optimizations that you could choose from? So the ported code from the DPCT tool is pretty explicit or verbose when it provides comments. There's something called a cyclomatic. So DPCT is its previous name. So they market it again to cyclomatic. Intel has this way of renaming things as they evolve. Cyclomatic is an open source project. So the compatibility tool is an open source. Again, DPCT, when I say it, it's from Intel product, closed source, just an executable. Cyclomatic is the same open source, is the same as DPCT, but an open source project. You can build it on your own on Polaris or any NVIDIA system. So ALCF Polaris also has this cyclomatic tool along with which is part of One API upstream module. So the simple process is you have a CUDA code, you migrate it with this cyclomatic tool or a DPCT tool. You have something called as C++ with SYCL. This is an intermediate SYCL source code once you get ported. I wouldn't say it is completely optimized. You would have to do a lot of cleanup, but this should be ready to deploy. So most folks who port from CUDA to SYCL just right away run this on the hardware if they can. Most of the times they can, just to check for the correctness. And the next step is to actually optimize it. So I'll show you what optimize here means. So this is an intermediate code because it has a lot of dependencies with the DPCT project. It's not pure SYCL. So it's a mix of SYCL plus DPCT. DPCT, again, it's a tool or a project from Intel. You don't want that to be carried over into the production code, right? You just want the native SYCL headers and its APIs. So you need to take a ported intermediate SYCL code and clean it up. These are some of the instructions how you build again cyclomatic and access tool. This is just an optional. You could do it on your own. The instructions are also on the GitHub page. You should create issues if things are not working as you expect. They're pretty responsive. Let's jump to a SYCL tutorial in the meantime, before we move on with the other aspects. Sure. I can take any questions in the meantime. Okay. So I'll start with the source code that has MPI, OpenMP, and CUDA. This is one of the questions that we had earlier. How do you port such a project into SYCL? This is most, I mean, it's not the ideal case, but this is the most cases that we see in the HPC. So this single source, the single source code, excuse me, has MPI, OpenMP, and CUDA embedded in it. The way you compile it with on a standard, this is a compilation line on ALCF Polaris, and how you run it and bind it with the GPUs. So this particular code talks about like how you bind CPUs and GPUs to a given MPI rank. So this is just a simple hello world for HPC, I would say. So it has MPI with these MPI calls, MPI init, com, and the processor names. You have some CUDA environment variables to just query if you have any environment variables set, which is CUDA visible devices, if you have multiple devices, and also CUDA get device count to just get the count for number of GPUs on the node. Loop over each GPU available to a MPI rank and print its contents. And if you have an OpenMP attached to an MPI rank, and that will be printed as well. So switching, this cannot be compiled on Aurora because we don't have CUDA on Aurora. But I'll show you how to do it by porting this onto a SYCL code. So this is a project. So this is a GitHub repo, or you can find all the instructions and modules. So okay. One API modules are preloaded on Aurora. What is missing with porting from a CUDA to SYCL on Aurora is the CUDA headers, which are needed for the tool. So you would have to load a particular module, and which I have already loaded. So these are CUDA headers. The way you port it is pretty simple. You have a DPCT tool, the name of the source code, and the output directory where you want the ported project to be. Or sometimes you could provide extra arguments to find where the headers are, or where the dependencies for the source code is. So you could include that. You get a bunch of warnings. As I was saying, DPCT is pretty verbose. So it provides verbose information of where things work and if things can be ported or can be ported. You could see there's a directory created. All the projects that are ported will have an extension called dp.cpp. So this is the one code that I got ported from. On the left-hand side is the ported project, and I'll open the code from CUDA. So the first thing to observe is the headers. One notable change is CUDA runtime is swapped now to two different headers, SYCL and DPCT. DPCT is not the standard header. It is just from the tool. So you would have to remove it for the production or for any optimizations or for a cleaner code. SYCL.hpp is the standard header, as you all know. And the rest of the headers are pretty much the same as the original code. You don't have any source code changes in the first function. This is just a standard CPU. Let's jump to the main. No changes with the MPI. So you have CUDA visible devices. Of course, this would not work on Aurora because CUDA visible device is very NVIDIA specific environment variable. We have something called a Z affinity mask. So you have to make the change. Okay, so as I was saying, there are few CUDA APIs like CUDA device get count and CUDA get device properties. These needs to be ported. So it'll be equated to DPCT device count and DPCT get device info. So like the toolkit will provide you one-to-one equivalence when available and port all the source code. So you have the one OpenMP code as well, which gets ported. Let's see if, I mean, this should work because I've tested it on Aurora. Let me get a, so I've just shown you how to port it on the login node, but I'll have to get a compute node to show a demo. Good questions. Okay. So we are on a compute node. Let's compile this. Since we have a ported code with SYCL, OpenMP, and MPI, we're using MPI compilers, with FSYCL being the standard SYCL flag, and cuOpenMP being the OpenMP flag to compile the source code. Okay. So how do you run it? And Aurora has multiple GPUs and a CPU. So we have to use MPI exec. Go to the README. Easier to do it. So I'm using one OpenMP thread. These are some of the instructions that you could find it in the Aurora guide. How do you run the project? Okay, I'm running here with the 12 MPI ranks. I'm binding with a specific combination of CPUs for each rank. GPU tile compact is a script that is already available on everybody's path on Aurora. This just says how to use each tile of a GPU, and it binds to a particular rank. So this is nothing but how do you bind the CPUs and how do you bind the GPUs to a given MPI task. Okay, so you can see I run with 12 MPI ranks. You could see the ranks in order with one OpenMP thread. So the thread ID is 0. And you should see what is the hardware thread that a given MPI rank has access to. So this is the range. And what is the actual hardware thread that particular MPI is actually using, or the OpenMP thread that is being used. the node host name, GPU runtime ID. Since we bind a given GPU to an MPI rank, this is all 0. You should see here, like the GPU ID is not available and the bus ID is garbage. And I'll tell you why. Let's see in the ported code. On the left-hand side, you have a ported DPCT source code. And on the right-hand side, you have the CUDA original source code. On the CUDA side, you print the bus IDs, which is the device CUDA from the CUDA device properties. On the SYCL side, DPCT actually commented that there is no such device property exists, similar to PCI bus ID. So you get garbage. So this particular prop.pci bus ID is replaced with -1. And that's the reason you just get some garbage results. Luckily, as I was saying, there are, I mean, it's not complete one-to-one mapping or port. Luckily, you have there's a way to get that functionality in SYCL from standard APIs, or sorry, from the extensions from Intel, DPCP. Okay, this particular piece of logic is missing, and SYCL actually came up with this extension where you can query for the PCIe address. So the particular in this particular GitHub repo, I have replaced the PCIe bus logic and as well as the Z affinity mask, which should give visibility of all the devices, device ID, and its PCI bus ID to recognize the device. So let's compile this project with the modified source code. Okay, now you can see some valid information for the GPU ID and the bus ID. So on Aurora, you have 2 tiles. So for each GPU, so you have 0, 0.1, 1, 1.1. Similarly for all the 6 GPUs. So there are 12 tiles. The bus ID is common for both the tiles. So you have 6 distinct tile information. So this way you can port a CUDA code with a mix of various programming languages into SYCL. And of course, you need to do some modifications for the code that you cannot port. Switching back to the slides. As I was saying, if you run the code, CUDA code on Polaris GPUs, this is how you see the output. There are 4 GPUs. The runtime, this is the binding logic where it says bind 1 GPU to a given MPI task. Okay, and you get the range of CPUs that are visible to the MPI. So when you port, you need to see what are the areas that you need to check whether the DPCT toolkit has ported or not. So these are the 2 APIs that we look for. We just swapped CUDA visible devices to Z affinity mask, and CUDA device properties was not able to be ported by the toolkit. So we had a SYCL equivalent, just an extension, and this is how you see the garbage output. And this is how once you make the change, you see the right or some valid output. Below is the reference to to the Aurora documentation where you find the appropriate binding information for CPUs and GPUs. Binding is again a very important task when you run it on the HPC systems. This is not common to Aurora. It's applicable to any DOE system or any machine that you can, any HPC system in general. There'll be a talk today by Vitaly again. He will speak about some of the performance implications if you don't do the binding. Well, possibly. So some of the common mistakes you can come across when porting to CUDA to SYCL. The most common one is, again, I was earlier saying about the XYZ dimensions, which naturally gets translated to 0, 1, 2 when you port it to SYCL, but it is not. It should be inverted to 2, 1, 0. This is the most common pitfall that in the earlier days we have used. So we have come across. This did not bite us much because XYZ dimensions are pretty much the same. So even if you have 0, 1, 2 or 2, 1, 0, it didn't matter much in terms of correctness, but the performance was really bad because you have indexing in the wrong, slowest dimension if you have an incorrect. So yeah, there are two possible side effects. One is incorrect answers, which is the worst case. Second is the performance degradation, of course. The second is synchronization semantics. Okay. So let's say you have a source code like this, where you have 0 to 9 threads doing a synchronization. Okay, only part of threads would do a synchronization. So as I was earlier saying that CUDA has a concept of warp. So 32 threads exist for this particular logic. Only threads with IDs less than 10 would do a synchronization. Rest of the threads from greater than 10 would just go to the next piece of code. This particular piece of code is not correct. It can lead to a potential race condition because some of the threads are doing synchronization, some are not in a given warp. This is this is an undefined behavior, but it is still allowed in CUDA. So you can potentially lead to a race condition, but it doesn't hang or give you a wrong answer. Because CUDA allows threads to proceed even if they don't synchronize in a given warp. When you port the same logic to SYCL, that does not apply, but you can still port it. So we have many apps even today that ported the similar logic and have seen deadlocks because SYCL does not allow conditional synchronization. So when you do a SYCL group barrier, which is equivalent to a sync threads, it would synchronize all the threads in that particular warp or a subgroup here. Okay, so this particular piece of code would not work. It leads to a deadlock. Luckily, there is some guidance, or the specification has evolved. Thomas is part of the specifications committee. So you can query for what are the active threads that are part of this logic, and then just pass those active threads to get to the barrier. Okay, not everything. This way you can avoid the deadlock. So how do you get the active threads? This is the API to get the active threads. So this is not so straightforward, but you should be really careful about when you encounter such a logic or when you see deadlocks. This is the most common example of the deadlock when porting from CUDA. Oh, the second one, this is my favorite, the CUDA memory in CUDA, constant memory in CUDA. So kernels have been optimized for years using constant memory because that provides the fastest cached access for all the threads. The concept of constant memory does not even exist in SYCL. It used to, but they have removed it from the specification, and I'll talk about why. So with the use of constant memory in CUDA, it provides uniform access to all threads because the value in the constant memory does not change. So all the threads can access it instantly, and it's much faster access than global memory. Again, this is a separate piece of hardware even on the NVIDIA side. The SYCL side, you don't have a concept of constant memory. All the memory spaces are abstracted differently in the SYCL side. So having a constant memory model is not so a common task in SYCL, or it does not even allow right now. So there are two possible solutions. These are not, again, so straightforward. One is constant variables. So the variables that are constant and the values are known at the compile time. And second are the variables whose values are dynamically assigned at the runtime, but they still stay constant at the runtime. So yeah, so for the values that are constant, let's say whose values are known at the compile time, you could just use C++ semantics with a constant expression and then assign these values. So these will be absorbed into the device code in line. So you don't have any issues with it. And these will still act as a constant memory inside a kernel. The actual problem is when you have a device, like a constant variable on the device side, which are dynamically assigned. So you assign it at runtime. On the CUDA side, you do a memcopy explicitly. So such a thing needs to be, so device global is not a part of SYCL specification. It's an extension to just cover that particular pitfall with constant memory. So you could do very similar things as constant memory, but the APIs and the ease of API is not so straightforward as constant memory. There is a lot of limitations as well, but you can get work around with it. This is my second favorite, the CUDA free. As you can see, you allocate some memory with the CUDA malloc, you run it on a kernel, and you do a CUDA free. This particular CUDA code does not have any issues. It could run perfectly fine. The reason is kernel launch is an asynchronous task. So when you hit CUDA free, the memory is being freed. But before that, it'll be synchronized. So there'll be an implicit synchronization behind the scenes. So the idea is with the CUDA free, you do an implicit synchronization with the device. All the kernels that previously used the memory will be done. It guarantees that no running kernel will access the freed memory later. The bottom line is you don't use that memory once it is freed. That's the goal of having an implicit synchronization behind the scenes. In the SYCL side, you don't have such an synchronization. If it is a free, it's a free. It does not matter whether the particular memory is being used or not. So when you do a SYCL free, it does not do synchronization. So operations that are still on queue could be freed, and that can lead to undefined behavior and or crashes. So once you free the memory and you use it later, it's garbage in both CUDA and SYCL side. But if you translate this CUDA code to a SYCL code without synchronization, this would lead to an undefined behavior, just because the data would be freed even though when the kernel is still being executed. Talking about warp intrinsics, as I was saying earlier, CUDA offers a lot of warp intrinsics, and they all assume that the sizes are 32. So there are 32 threads per warp. SYCL replaces these warps with subgroups in the abstractions, but subgroup size is not 32. They are device dependent. So it's not particularly 32. So when you port something from CUDA to SYCL, so there is still a lot of production code which uses this particular piece of logic on the CUDA side because it's safe, because there's no warp size other than 32. When you port this particular piece of code to a SYCL side, it might not even work properly. First thing is it might lead to incorrect results. Second is the performance degradation. So direct translation of warp intrinsics is so translating this particular logic to SYCL is incorrect. So you could use warp intrinsic functions, which does not take into account the size, or which does not assume the size, in other words. So you have a shuffle, you have a shuffle sync or shift group left. These are the equivalents. So there is a table of what are the equivalents for the warp intrinsic somewhere on the project website. So how to manage the unsupported APIs? So DPCT provides a lot of warnings when it cannot port a certain API. There are certain experimental extensions. We just used one, which is the PCIe address from SYCL. When there is absolutely no way to actually find an extension as well, and when there is no way to find a port from a native programming model to a SYCL. Native can be a SYCL or HIP. There's something called as interoperability in SYCL, where you can obtain CUDA, HIP, or level 0 objects and place it inside SYCL. So let's say you have no way to work with a CUDA string. You can query for a CUDA string in SYCL and just directly use CUDA string to launch any CUDA API inside SYCL. So this is the way of providing interoperability. It's a pretty powerful feature. Thanks to Thomas, who have advocated for it. And when porting PTX or assembly for NVIDIA hardware, feel free to reach us. A few of us have ported some of this code, and as well as Intel provides a pretty good resource of helping us with porting these corner cases of PTX and assembly source code. Again, this is just cyclomatic instructions. So things to consider when using cyclomatic. It's just a tool to bridge between CUDA and SYCL, not for a production or on an optimized code. So as you can see, there is plenty of DPCT namespace. This is not standard. Again, it's not a standard as SYCL. So there'll be DPCT headers and namespace, which you should avoid using it in cleaner code. So the option is to just find the equivalents of DPCT and replace them with SYCL, because DPCT is nothing but underlying SYCL. So how do you access these tools on Aurora or Polaris? So these are some of the instructions. This is a quick compilation line of how you use SYCL compilers on NVIDIA and AMD GPUs. It's a C++ 17 base standard, so you should mention that. Or I mean, the SYCL is already compliant with C++ 17, so you don't need to explicitly mention. FSYCL is still a major flag. This FSYCL target is the way that you say to the SYCL compiler that I'm targeting NVPTX backend, which in other words means CUDA GPUs. You can also pass the architecture. Similarly, for the AMD, you say that it's an AMD GCN backend, and you can also pass the architecture for the AMD GPUs. So I'll just briefly go over some case studies. How do you transform a trust API, which is parallel STL for CUDA? So there are equivalents in SYCL called as 1DPL project. 1DPL nothing but looks like a standard C++ STL algorithms. So as you can see from majority of the arguments, these are pretty much very similar or exactly the same like C++ STL. The one exception is the first argument being policy. This policy is nothing but Q. Remember, I was saying you should pass a Q explicitly to each and every API of SYCL, and that particular sticks with that as well for this project as well. So 1DPL adopts, as I was saying, C++ algorithms. So 1DPL is how is 1DPL portable? So since it uses SYCL kernel underneath, and SYCL is portable, it just makes 1DPL portable as well. So you can use the same transform, reduce, standard SYCL, C++ STL APIs on all three hardware. Talking about some math libraries from CUDA, so you have cuBLAS SGEM, which gets transformed to a 1MKL gem call. Much of the APIs are pretty much the same, irrespective of whether it is like a cuBLAS or a 1MKL. They pretty much all follow the same conventions. Of course, there are some stark differences with the arguments. You have a handle, which again is tied to a stream, but in here you can directly pass a queue. I should mention here that we need to explicitly map it to a column measure, because 1MKL provides both column measure and a row measure because of CPUs and GPUs or Fortran. cuBLAS is inherently C based, so it's column measure. So you have written types. You have cuBLAS status, which just tells the error handling. And on the other hand, you have an event, which again tells us about whether the particular task is complete or not. So again, these are just differences with how the APIs look like. So you have a dependency. Again, you can chain dependencies by passing event to these APIs again. So these are from 1MKL. 1MKL SYCL APIs also take dependencies like a standard SYCL API. I was just showing you about an individual project where you take a single source code and port it to SYCL. But in real life, majority of the projects are like a lot of CUDA files. So I've just shown here what the Autodoc project looks like. There are lots of headers with a lot of .cu files. You can't just manually port each and one of them. But DPCT can port entire project at once. And all the ported files would have some sort of an extension like this, .dp, .cpp. So it's a pretty powerful and handy tool. Before we conclude for today, I'll quickly go over cuBLAS porting and cuFFT porting. It's pretty simple. So you have a cuBLAS gem API. So again, these are the examples that are taken from CUDA samples, CUDA library samples. So you can just take any of the examples from CUDA library samples and translate it yourself. As you can see, you have a CUDA-based headers. Okay, cuBLAS APIs.
Abhishek?
Yep.
We are still seeing the case study 3 slide.
Oh, thank you. Sorry. Okay, can you see my terminal?
Yeah.
Okay, sorry about that. I'll just back up here a bit. So I've just opened the file under cuBLAS in the repository, from the repository. So these are, again, standard CUDA library samples. When you port a code or any project, you just query for what are the CUDA or CUDA specific APIs. So I'm just seeing that there are certain cuBLAS APIs, cuBLAS gem. So these are the lines that I would target for porting, right? So again, you could do the same thing. And the instructions are in README. The line is pretty straightforward. So I've already ported it. So let's check out the code that is ported and open it side by side with the original source code. Talking about the headers, yes, they are replaced with the DPCT and the standard SYCL headers. You see a lot of DPCT namespaces. This is just to handle the creation of device and the queues, which I believe you do it here as well. Yes, cuBLAS and cuStream. Okay, the transpose now is ported to MKL. Gem calls are now ported to MKL as well. You have CUDA mem copies. Now they are ported to SYCL mem copies. There is a synchronization. Yes, there is a stream synchronize. There is a queue wait synchronization. So the entire project is now ported to SYCL, but it's not so elegant because you have all these non-standard headers and DPCT namespace. Okay, you can run this readily, CPX, fSYCL, because it's a SYCL source code, QMKL, cuBLAS, gem. Of course, you get a lot of warnings because it's from the tool and they are not standard. You can clean it up later. Okay, so DPCT can handle libraries as well, and I'll quickly go over some of the cuFFT, which is the slightly advanced version. Again, it has the same source code. So you have the headers specific to cuFFT and cuFFT specific calls. So you should be looking for how are these APIs ported to its SYCL equivalents when you use the tool. I already ported the code. Let me just open it side by side. The headers are changed. You have device creations and the stream object. So all these cuFFT equivalents are now ported to DPCT equivalents. Of course, which piggybacks on one MKL behind the scenes. So, okay, as a bonus, I have cleaned up this DPCT code to a standard SYCL API. So let's see how does that look like. So you have less headers. There is no use of DPCT at all on the left-hand side. So on the left-hand side, you have a standard SYCL source code, which uses standard SYCL APIs and one MKL. On the right-hand side is the source code that you just portrayed. So you don't have all these stream creation because they're just done by one line. You use standard 1MKL APIs, not the DPCT equivalents. So this is much cleaner, I would say, I hope, than the so it's about half the lines as the ported code. I mean, of course, it has a lot of comments as well. So yeah, one would start from cleaning up a ported DPCT code to its actual SYCL equivalent in the production world. That's my last demo, and I'll briefly go over the resources that we have. So this is some performance data. This is very old, I would say. This is SYCL running on NVIDIA GPUs on Perlmutter. I've run on 4 GPUs. So the orange bar is the SYCL. So the timings means SYCL is slowest. Again, this is from at least 2 years ago, and things have changed a lot. So SYCL, it's not a small source code. It's end-to-end NWKMX application. So it consists of a CPU, many dependencies. The runtimes are quite large, as you can see from the time. You could see an end-to-end source code running on SYCL running on production machines like Perlmutter, and we have run it on Polaris as well. It's exactly the same hardware. I've shown here 2 different SYCL versions. So one is DPCPP, which is Intel LLVM implementation, and one is HIP-SYCL or adaptive CPP from University of Heidelberg. The HIP-SYCL one is much faster and better, but still poor in performance than CUDA. Things have changed a lot. Again, CUDA is not 11.5, it's 12.8 these days. But this is from the old days. It talks about the functionality and performance. So functionality is already pretty stable. So you don't have things that don't work on other hardware from SYCL side. So this is from the ALCF frontier again. This is again quite old data. We have run it on 120 nodes. So we just show you how the differences looks like. So here on the CUDA side, HIP-SYCL is fastest. On the AMD side, Intel LLVM is fastest. So there are subtle differences when you run SYCL on other hardware platforms. And this is my last slide. So the just provides you some guidance on how to use the tool, what are the available resources, and documentation links. Thank you for your time.
Thank you, Thomas and Abby. I know there has been a lot of questions in the chat, but now is the time. If you guys want to unmute yourself and ask questions, feel free to do so. We will be providing the slides, and since a lot of questions came in the chat, I'll try to include the chat as well.
Maybe I have just one last remark, just to to continue to blurry even more the message. It's like it is possible also, if you really want, you can use CUDA directly on Intel, right? We have some project who do that. So it's porting from CUDA with a level 0 backend. It's called ShipStart. So, and it is also a possibility. Oh, so this is why I think, yeah, it really depends what you want to do. So SYCL, the good thing is like, for some people, is like it's a little higher level, like it's a convenience wrapper, let's say, around give you nice C++ stuff. So for some projects, this is exactly what they want. Some project maybe they won't even go even higher. They want more to do like Cocos or stuff like that. But maybe also some project would just want to say at the kind of low level CUDA kind of stuff. And in this case, we have like a ShipStar. So I think it's really hard for us to advise on what you want to do. For example, me, of course, I will advocate for SYCL, but some other people advocate for Cocos and stuff like that. But it is just you as an application developer what you want to do and stuff like that. And we hope at least here we show you one possible path, show you the advantage and maybe the disadvantage of SYCL, and then maybe now you have more information to do an educated guess. So hope it was useful.